that.
Oh.
And I am pleased to introduce, well, no, wait, let me make two quick comments. One is we're still working on what the format for the fall 2021 Algebras and Rings in Colorado Springs seminar will look like. We're guessing it'll be some sort of hybrid of a few online talks and then some in-person talks. So I'll be sending out an email over the summer to let you folks know what that will look like. If you would just, I won't ask you to mute yourselves, but just go ahead and sort of be aware of whatever sounds might be blasting through the microphones on your end during Ben's talk. And okay, now I'm pleased to introduce Ben Steinberg of the City College of New York CUNY Graduate Center, who will speak today about Cartan pairs of algebras. Ben.
Okay, so I'd like to thank the organizers, Jean and Zach and Mark and whoever else is organizing, for giving me the chance to be back, so to speak, in Colorado. It's always nice to be talking here. So this is joint work with, as you see, a large collection of authors. We originally kind of started as two groups, and then when it became clear that we were working on the same thing, we decided to join forces, which I think was a good thing. I think instead of having two papers of a certain level, we had one much better paper. So I think that joining forces is a good thing. I also think that there will be, for the experts, and there are some experts, that there will be several lies told during this talk. So sometimes I've oversimplified things in ways that people who are experts will know what I should have said, and people who are not experts will be better off not knowing. So if you're an expert and you say, hey, wait, he's cheating a little bit, there's a couple of little cheats here and there, but it's just to make the talk more understandable. So I do apologize in advance for sometimes cheating to make the definitions more digestible. And sometimes there are little caveats, and I won't always tell you, but if you're an expert, you know, and if you're not an expert, you'll be happy with the way it is, hopefully. Okay, so here's my outline, but I guess nobody actually reads outlines. So we'll skip them. So here's the part of the talk that I'm completely unqualified to give. And so the experts in the audience can tell me where I'm wrong, or maybe wait till later, tell me where I'm wrong, because I know nothing about analysis. I'll just say that right off the bat. I should have taken analysis classes, obviously, but I didn't, so here we go. So in the 60s, Feldman and Moore studied Cartan pairs of von Neumann algebras. It's quite interesting because I've known about this paper for years because people who do group theory, which I normally hang out with, always talk about this theorem about these Borel equivalence relations all coming from group actions, these with countable classes. And this was coming from essentially the part one of the same paper. But now I'm interested in the other part. So a Cartan pair basically consists of a von Neumann algebra A and a maximal abelian subalgebra B, which gives you the cool acronym MASA, although I would normally say commutative, but that wouldn't give you a very cool acronym. Maximal commutative subalgebra, I don't know. And then there are some constraints that say roughly B fits nicely in A, and these constraints are both algebraic and analytic, and I'm in no ways qualified to tell you about them. But you'll see, if you're familiar with the stuff when we do the algebraic theory, you'll see like analogs of most of that stuff here. And what they prove roughly is that all Cartan pairs come from some sort of twisted groupoid algebra. In fact, the groupoids that arise are actually equivalence relations, so they're very special. And there's a measure structure on these groupoids, and I'm not getting into how that works. But roughly speaking, they come from a groupoid, and the commutative algebra, the maximal abelian subalgebra, are functions on the unit space. So these are certain kinds of functions on some groupoid, which is actually an equivalence relation. And there's some measure stuff involved in order to be able to make it all work. And then it has this commutative subalgebra. And the groupoid and the twisting are uniquely determined by the Cartan pair, you know, up to some equivalence. So these twists are determined by some cohomology theory. And I'm again not qualified to say much. Now, Kumjian and Renault then created later on a C-star algebra version of Cartan pairs. And I'm kind of over summarizing the history. Renault has sort of a version 1.0, which wasn't 100% satisfactory. So then Kumjian came out with kind of 2.0, and then Renault came up with 3.0. That's more or less my understanding of this. Maybe there's a 3.1 right now, and I haven't been updated yet, or someone's beta testing it. I don't know. And roughly speaking, C-star Cartan pairs come from, again, twisted algebras of groupoids for certain special kinds of etale groupoids, which I'm not yet going to explain what those are. These are just words for the moment. And again, the groupoid and the twist are unique in some appropriate sense. Now, I think I'm not an operator algebraist, so operator algebraists are probably always excited about this, but I think in recent years, there's been some extra excitement about this because of some results starting with Matui and Matsumoto in 2014, where they basically showed that this Cartan pair algebra lets you get nice interpretations of some things from symbolic dynamics, another area which I dabble with, but I'm, again, not qualified to say anything super special. So to any finite directed graph E, you guys in Leavitt path algebras like to call it E, so I'm calling it E. You associate a certain symbolic dynamical system, which is called the shift of finite type. Roughly as a space, it's just all the infinite paths in your graph, and then the shift map lets you remove the first symbol from an infinite path. And it's been known for a long time, to those who know these things, that there's connections between the shift of finite type, the associated graph C-star algebra that you get from this graph, and the associated Leavitt path algebra. So the most famous example is that in symbolic dynamics, Bowen and Franks define something called the Bowen and Franks group. And this turns out to be the K0 group of the graph C-star algebra and of the Leavitt path algebra, at least under recent, maybe you have to avoid some trivial conditions, but more or less that's true. And under condition L, which is one of these conditions that if you do this stuff, you know, and otherwise I'm not going to explain it, but it's some popular condition in this theory. The graph C-star algebra and its so-called, sometimes it's called diagonal subalgebra. It's algebra of subalgebra of continuous functions on the path space form a Cartan pair. For those people who do Leavitt algebras, let me just tell you what is this commutative subalgebra. So I'm going to use the Leavitt algebra kind of notation because I'm an algebraist. So to each path, you have a certain idempotent, which I'll write P star, which means you do the path P, and then you do the ghost path. And the paths of this form generate a commutative subalgebra. And that commutative subalgebra can be identified with locally constant functions on the path space. And then if you complete everything and go to the C-star world, you'd get all continuous functions on the path space. So anyway, so if you're an algebraist, you should think in your mind the algebra generated by paths followed by their ghost path inverse. And that's roughly what this commutative subalgebra is. Except in the C-star setting, it's completed, and in the algebraic setting, it's not. So Matui and Matsumoto, who've been reduced to MM, for instance, showed that a certain equivalence relation on shifts of finite type called continuous orbit equivalence are basically determined by and determine the isomorphism class of the Cartan pair. When I say the isomorphism class of the Cartan pair, I mean you have to keep track of both the big algebra and its maximal commutative subalgebra, it's Cartan algebra. They're called Cartan subalgebras because in Lie algebra theory, as probably most people know, maximal abelian subalgebras are called Cartan subalgebras. So that's where the Cartan word comes from. Okay. That's the only mention I'll make of Lie algebras because I can't deal with non-associative things. And more generally, it was shown that flow equivalence, if I'm correct here, of shifts of finite type is determined by a Cartan pair, but it's not from your original finite graph. You have to do something that makes the graph infinite so that you can kind of take into account stable isomorphism. So I believe this was my understanding from looking at the operator papers. Hopefully I'm not overstating the theorem. And maybe you need, again, some conditions. So a natural question that I think arises is, can you work with Leavitt path algebras, LPAs, instead of graph C-star algebras? So can you encode the same phenomena from the Leavitt path algebra and its corresponding commutative subalgebra so you don't have to go to completed things that I don't understand? So LPAs are what are sometimes called Steinberg algebras by very generous people, mostly living down under, of ample groupoids. So, so I haven't said what an ample groupoid is yet, but I will. But anyway, there's a series of work done by a number of people, Brown, Clark, and I can never say it correctly, Anif. Hopefully that's close to correct. But then there was another work by Boza, Hasrat, and Sims. Then there was, I think, more general work done by Carlson and Rout. And I think the most general work was done by me on this thing. But again, I mean, I was building off all the people before me. And what these works basically showed is that the groupoid of a Leavitt path algebra can be recovered from the Leavitt path algebra and the locally constant maps on the path space of the shift of finite type or the graph. And again, that algebra is exactly the algebra generated by the idempotence PP stars, where P is a path. So they're the natural commutative subalgebra that everybody who does Leavitt theory knows about. And people kind of know it's connected to Cantor sets and stuff like that. So it's exactly that. And in the algebraic setting, here's the bonus you get. Condition L you don't need. It's completely unnecessary in the algebraic setting. So it turns out that you need condition L for it to be a Cartan algebra in the traditional sense of being a maximal abelian subalgebra. But in the algebraic setting, you can get away with a little less and still recover your groupoid. And we're going to call them in this talk quasi-Cartan pairs. When this original work was done, nobody had a name for them. But anyway, condition L is not important here. I should also mention there's a beautiful result by Carlson showing that if you work over the integers and if you view your Leavitt algebra as a star algebra, so you keep your involution in your brain, then actually star algebra isomorphism already gives Cartan pair isomorphism. And so you can really see the groupoid from the star algebra over Z. So this is kind of a theme. You know, working over Z is actually better in some ways because Z knows about every other field and it also knows about the C star algebra. Of course, working over Z means you have prime numbers and the integers and number theory thrown in your face. So that might be a bad reason to work over Z. Okay, but what was missing in all this previous work 1 through 4, is an abstract theory of Cartan pairs. So people just worked with groupoid algebras and said, can we get back our groupoid? They didn't say which algebras, you know, which pairs of an algebra and a commutative subalgebra actually come from groupoids, which is something probably we should have done earlier, but we didn't. Okay, but I'm an algebraist. I might be able to pass a multiple choice exam on Blackboard about C-star algebras, but I would fail a written exam. So let's move to algebras. All right. I might even only get a B on the multiple choice exam if you try to make it tricky. Okay, so let's start with groups, because groups are, whatever an ample groupoid is, a group is a one object groupoid. Okay, so it's a group is a groupoid with one idempotent. So we should start there, because people have been studying group algebras for a long time. So let G be a group and R be an integral domain. So first of all, because I saw some co-authors on the list, in this talk, I'm going to always make R an integral domain to make things a little bit simpler, but in the real paper, we just require R to have no idempotence except 0 and 1. But just so to avoid some technicalities, I'm going to say integral domain, and you're not going to lose very much. So the classical isomorphism problem for group rings goes back to the 1940s. You can already kind of find it in Higman's thesis from the 1940s, and it asks, if Rg is isomorphic to Rh, where G and H are groups, as R algebras, must G be isomorphic to H, right? Seems like a reasonable question. Of course, the answer to this question is no. Oh, I got ahead of myself. This is the simplest state-to-state version of what we would like to know for groupoids. But unfortunately, the answer is no, because if you have two finite abelian groups of the same order, then their group algebras are isomorphic by basic Fourier analysis. If you're an analyst, this is the one part of C-star algebras I know, finite dimensional ones, or basic Frobenius style representation theory. I think Dedekind already knew this fact. So you cannot recover a group from its group algebra in general, but that's because the complex numbers are way too big. So a more hopeful, reasonable question to ask is whether ZG isomorphic to ZH, also known as ZG isomorphic to ZH, in case you need translations from other parts of the world. I'm bilingual in this because I was in Canada for a number of years. So it's more hopeful to ask that this isomorphism implies G is isomorphic to H. Why? Well, as soon as the integral group rings are isomorphic, then every other group ring is isomorphic because they're just extending the scalars. So this is your best shot. If this guy cannot distinguish the groups, nobody can. So there was a long period where people tried to show that for finite groups, which was all people cared about in the 1940s, I guess. Many people tried to show that, in fact, the isomorphism problem had a positive answer for finite groups. There was a lot of positive results. For finite abelian groups, you can distinguish the abelian groups by their integer algebras. Then they went up the hierarchy of finite groups. But in 2001, the dream was shattered. I think by Brouwer's day, they already knew it wasn't true. They just didn't know how to find the example. So Hertweg found two non-isomorphic groups of order 2 to the 21st times 97 to the 28th. Those are not typos, with isomorphic integral group rings. And I'm sure this was not found via computer search because that's a big group. That's a big size for a group. So he knew what he was looking for, obviously. So he found this counterexample. So you cannot, for these two groups, you cannot recover the groups from their group ring no matter what base ring you use. You're just in trouble, no matter what you do. Okay, so how do you get positive results about group rings? So I'm basically going to explain the main idea of this talk for group rings, and everything else that we do is going to basically be the same, but it's harder because you're dealing with topological groupoids, but the moral is the same. Okay, so there's only one method I'm aware of to show that a group algebra determines its group. So if you have a unit in your ring R and you have a group element, then when you multiply your group element times a unit, you get a unit because the inverse is just U inverse G inverse. So that's not rocket science. And these are called trivial units. And we say that RG has no non-trivial units if every unit is trivial. And you can actually make, and we want to make the same definition for twisted group rings. So twisted group rings, I originally thought was some sort of rock band from the 1980s. Sorry, making that Twisted Sister joke, but okay. So twisted group rings. So again, for twisted group rings with only trivial units, you can recover both the group and the twist from the group ring, from the twisted group ring. So let me remind you what is a twisted group ring. So a twisted group ring, to define one, you start off with a 2 cocycle, which I will not tell you what it is now because I'll tell you what it is later for groupoids. But anyway, maybe you know about these things. And normalized just means that when you plug in 1, you always get 1, 1, you get 1. So the twisted group ring has a basis in bijection with G, and since I'm working with analysts, we call them delta Gs. And the product is, instead of doing the usual group ring product, you twist it by multiplying by this unit. Remember about that, my cocycle only takes values in units. So if C is trivial, meaning it takes on only the value 1, you get the usual group ring. And because C is a unit, again, the multiples of elements of G, which are now called U delta Gs, will be units again. The inverse will involve the cocycle, but anyway, this will be the case. And in fact, we get a central extension. So inside of the units, we have R cross times delta 1. Then we have my trivial units. And if I quotient out by the scalars, I get G. And this is exactly the central extension, which is classified by this cocycle. So there's a bijection between central extensions and cohomology classes. This is basically what they teach you in group cohomology. And I'll say that the twisted group ring has no non-trivial units if the only units are these obvious ones, units times a delta G. And now I'll show you how to recover the twist. So I'll give you the complete proof for this special case so that you'll believe everything works for groupoids, because the idea is essentially similar. So imagine that you have a twisted group ring HC prime. I was going to make a joke about a twisted group ring pin on your uniform, but there are probably too many young people here who didn't watch Twisted Sister videos like me. Okay, so we have or older people who didn't watch them, one of the two. Okay, so we have an isomorphism from a twisted group ring to RGC. Then this exact sequence for H maps to the one for G. Why? Because G has only trivial units, Rx.H has to go into the group of units for this group ring RGC, but those guys are all trivial. So you actually get this diagram because this guy has only trivial units, so there's no place else for these guys to go. And it's an R-algebra isomorphism, so it's 1 here. And this is injective, but since the guys from H span the group ring, its image has to span Rxg, which means you have to get all the lines through elements of G. So therefore, this must be onto. If you miss some element of G over here, you'd miss a whole line in this free multiple. So you'd miss somebody. So that's roughly the idea. So we can actually recover G and the cohomology class, the extension, from a group ring isomorphism. Okay, so that's how I thought about all this stuff when I was doing just the case of untwisted groupoids. So now you have to ask yourself, well, which group rings have no non-trivial units? And had I given this talk a few months ago, what I'm about to say would be totally different. So it's funny how progress changes. So if G has something called the unique product property up, then this group ring has no non-trivial units. I'm not going to define the unique product property because it's a bit cumbersome. But if you have a group which is left orderable, so it admits a total order which is compatible with left multiplication, then it has this UPP property. So this includes any torsion-free abelian group, a free group, a braid group. There are gazillions of groups. Thompson's group F. Name your favorite torsion-free group, and there's some chance it has this property, but not all of them do. And any UPP group is torsion-free, by the way, whatever that property means. Now, Higman in his thesis proved that if Z, also to give you examples which are not torsion-free, Higman in his thesis proved that if ZG has no non-trivial units, then if you take the direct product with the cyclic group of order 2, which I'm calling C2, then you still have no non-trivial units. And he also showed if G is a finite abelian group of exponent dividing 4 or 6, or it's a quaternion group, then also you have no non-trivial units. So there are examples in the non-torsion-free world as well. So Kaplanski had a famous conjecture, which is actually due to Higman apparently in Higman's thesis, that says that if a group is torsion-free, then its group ring over an integral domain should have no non-trivial units. And this was the strongest of the three Kaplanski conjectures. It implies the idempotent, the no zero divisor conjecture and the no idempotent conjecture. But just this year, Giles Gardner placed on the archive a counterexample to the unit conjecture. So the last time I gave a talk on this stuff 3 years ago, I was under the impression that the stuff we're doing is going to apply fairly frequently, but maybe now it's not as good news because that means a lot less groups have this property. So his example, it has is a torsion-free group with a free abelian group of finite index. So from the group theoretic point of view, it's not very complicated. So in any event, it means the no non-trivial units phenomenon is less widespread than previously believed. Actually, my impression is that people didn't really believe the Kaplanski conjecture, but at least that one, the unit conjecture, that was the least likely to be true one because it was not known to be connected to any other part of mathematics. And the other ones are connected to things like, you know, Farrell-Jones and Baum-Cohn and fancy stuff. So they're more believable. But in any event, okay, so I guess that's all I want to say about it. So anyway, it's very interesting that he gave this counterexample. His counterexample is over the field F2, the two-element field. He doesn't have a counterexample yet in characteristic 0, but he thinks it's just a matter of messiness and not a matter of something else. I guess in particular, computers like better searching for solutions of equations over F2, I'm guessing. Okay, so now I have to tell you what is a groupoid. By the way, Gene, what time do I stop so I know when to start panicking?
5:30-ish.
So that's 7:30 my time, okay. All right, I can convert. So a groupoid is a small category in which each morphism is an isomorphism. So what does this mean? So you have a set of objects called G0, and you have arrows. And I'm going to view, because I've been persuaded by the analyst to do this, I'm going to view objects and identities as being the same thing. So the identity at an object X gives you the same information as the object X. And so just to avoid having multiple sorts, I'm going to do that. So G0 you can think of as either the object set or the idempotent set. In a groupoid, an idempotent is the same as an identity. And then you have a partially defined multiplication, which satisfies some axioms that tell you it's a category, and you have an inversion map. And from this viewpoint, this has always weirded me out the first time I saw analysts doing this. The domain is given by the rule, the domain of gamma is gamma inverse gamma, and the range of gamma is gamma gamma inverse. Why? Well, this is supposed to be, this should be the identity at the domain of gamma. But since I'm pretending that identities are the same thing as objects, it is just that. Okay, so if you're an algebraist like me, it probably takes you a while to get used to this viewpoint. If you're an analyst, you're like, why is this guy even having a problem? Okay, and I'm going to view GZ as a subgroupoid which consists of idempotents. So everybody's their own domain and range, and everybody is their own square. Okay, and then a group can be defined as a groupoid with a single identity. Do not try this in your first year algebra course. It will not go well, but that's how you can define a group. But to build interesting algebras from groupoids, we need to throw in topology. So this is where, it gets a little bit scary for people, but you really can't get anything interesting without topology that you couldn't do with groups. Okay, so a topological groupoid is a groupoid with a topology making multiplication and inversion continuous. And I'm going to assume in this talk, all groupoids are Hausdorff, which will make people happy except for Hui. And I'm going to give the unit space G0, the idempotent space, the subspace topology. And then because the domain and range are defined in terms of the product and the inverse, they're going to automatically be continuous. And the groupoid is called etale of multiplications of local homeomorphism. And that's equivalent to either the domain or the range being a local homeomorphism. Basically, as soon as somebody other than the inverse is a local homeomorphism, they all are. Okay, I'm not saying that's completely obvious if you've never thought about this. So unknown prehistory to most, etale groupoids were actually introduced by Grothendieck in SGA. You can find them in SGA along with lots of other stuff. SGA is the go-to random place to assign, results that nobody's going to ever look up. If you're in a paper, you're like, see SGA volume 4, and you're probably safe. Nobody will go there. So he introduced them to study toposes for those who are interested in such weird history. And a groupoid is called ample if it's etale, locally compact, and totally disconnected. So the term ample apparently was to describe groupoids was first used by Patterson because Renault had something he called an ample semigroup, which was big for what we're now calling ample groupoids. And I think Jean is not so happy with calling these ample groupoids, but since I don't have a better name, I'll stick with it. And notice because my groupoids are Hausdorff and etale that G0 is a Clopin set, which is useful to use. Okay, so let's give some examples because if you've never seen this before, if you're an algebraist, say, or an analyst who's never seen it, it seems bizarre. So first of all, a topological group is etale if and only if it's discrete. So if you like groups, then you're just looking at discrete groups. Why? Because there's only one object, and there's only one object, one identity, just the identity of your group. And the domain maps the local homeomorphism. So if you're locally homeomorphic to a one-point space, then even my topology skills will tell you you're discrete. Any locally compact, totally disconnected space X can be viewed as an ample groupoid by just making everybody an identity. So if you view it as a category, you have a bunch of objects in bijection with X, and then you have an identity morphism at each guy, and you have nobody else. Okay, and this is how you should think of a space as an ample groupoid. Another canonical example, if you haven't seen this stuff, of a discrete group GX on a locally compact and totally disconnected space, you can form the semi-direct product or the action groupoid or the Grothendieck construction, or this thing has more names than any other construction I know of in math. So as a topological space, it's just G cross X, and you should think of the pair GX as basically an arrow whose domain is X, its range is GX, and G goes from X to GX, and you compose them by multiplying. So basically, you're drawing the Cayley diagram of the action of G on X, and then you realize that there's a reasonable way to multiply this. So those are some examples. So then we have these groupoid algebras, which have gotten this name associated to them. And so we're going to start. I'm going to give you the Hausdorff case. So I guess basically, I think the semi-history of this is people have been looking at convolution algebras of groupoids over either the complex numbers or real numbers with their topologies for ages. I guess I started in 2007 or on Archive, or 2008. I put up a paper saying we should look at these over arbitrary rings and view those rings as having the discrete topology. And I started to systematically study them. A few years later, a group of people, including Mark here and some Lisa, Aiden, Cynthia Farthing, and I'm probably forgetting somebody because I don't have it in front of me, reintroduced them over the complex numbers, not realizing I had looked at them. But as I said, basically, if you know what to do over the complex numbers, I mean, the real numbers, it's not a big deal, but you can then start to study them and try to prove theorems, which is what has been done. So as an R module, so I use the notation RG, so that way it looks like the notation for a group ring. Now, analysts hate this notation because they think it's a free module on G. Back when I wrote this paper, I was still a category theorist, and I thought G was a pair, was a 5-tuple consisting of an object set G0, a G1, a domain, a range, an inverse, and a unit map. And so it didn't make sense to take the free abelian group on it or the free module on it. So it didn't occur to me that there might be confusion. Nonetheless, I think this notation is more compact and people will understand it from the context, so I'm sticking with it. But I think everyone else writes AR or G. So I guess you can either get the name or the notation, and I'll let you guys decide what you prefer. Okay, so the product is just convolution. So F star G on gammas, you factor gamma all possible ways and sum it, like you would in a group ring. There's a little elementary exercise to check that the sum is actually finite. So the actual story of this is I first learned about these groupoid algebras in Patterson's book, where the book is filled with integral signs. And since I haven't taken a course involving integral signs since I was an undergrad, I politely put Patterson's book aside and only read the chapters on inverse semigroups. But then I picked up Hui's book on the beaches of Tel Aviv, not his book, but his 100-page monograph on commutative C-star algebras, and he wrote sums. And then I said, oh, it's sums, I can do this. We don't need to be working over the complex numbers. So if Patterson had written sums, I would have started on this about 7 years earlier. So see, notation can be important. Okay, so now if we look at the algebra of G0, this is actually just the continuous functions with compact sub. So locally constant just means it's continuous for the discrete topology on R. That's what locally constant means. It means that each point each point has a neighborhood on which the function is constant. That's the same as continuous for the discrete topology on R. So if you look at the unit space, because the unit space is clopin, the compactly supported functions on the unit space live inside the compactly supported functions on G, and the only way you can multiply two units is when they're equal. So this turns into the pointwise product. So it's a commutative sub algebra, which we're going to use for our Cartan pair. And examples of these guys basically are like group algebras, Leavitt path algebras, inverse semigroup algebras, and matrix rings, and other stuff. As another example, if I have a group acting on a space X, and I form that semi-direct product groupoid, then the algebra I get is the skew group ring, where G acts on the locally constant functions from X to R by shifts. And then you take the skew group ring, which some people also call the cross product, but I think people in ring theory call it the skew group ring and mean something else by the cross product. So since this is rings, I'm going to go with the rings thing. So now I'm going to tell you about twisted groupoid algebras, and the experts here will know that I'm lying, but I'm just trying to make things digestible. So if you're an expert, you know what I should be writing. And if you're not an expert, you're going to be happy I'm not writing that. So if we have a groupoid, we can twist it by a locally constant 2 cocycle. So our groupoid has a topology. So it's pairs, G cross G has a topology, but we're actually only allowed to write down composable pairs because otherwise the cocycle identities won't make sense. And it's to satisfy the usual cocycle identity, which I like to write this way. Other people write it in different orders. So alpha, beta, and gamma will all be composable so that this will make sense. And that's the usual cocycle identity. And I want it to be normalized, which means that for every unit, CXX is 1. That's the obvious generalization of normalized from the group case. And then we can still, as the twisted group ring, which I'm going to write as RGC, analogous to my groupoid notation, is the same R module. It's the locally constant functions from G to R. But now we twist the product exactly like we did for the twisted group ring. So we sum over all products, which give you gamma, and then I twist. And because I made this cocycle locally constant, this will be a valid, legitimate, locally constant function. And you can check that. And the cocycle identity makes it associative. And the continuous functions on the unit space sit inside because this normalized condition says that if I multiply it, if I could convolve this guy at a unit, then this part doesn't play any role. The cocycle doesn't play a role. And these generalized twisted group rings, because twisted group rings are the same formula. And this is not the real definition of a twisted groupoid algebra. It's actually a more general construction, but the more general construction is more complicated. So this is sort of the Renault way of doing things in his first book, but then Kumjian realized that it's not general enough. So then he kind of generalized it. And but let me just say for the experts that if the groupoid G is paracompact, which will be the case if it's second countable, then because it's totally disconnected, this definition I gave here is equivalent to the general one. But we do have an example of an ample groupoid, which is not in the archive paper, but we do have an example, and we'll eventually add it somewhere, of a non-paracompact ample groupoid where this definition is not general enough. But it has to be non-second countable. For second countable groupoid, you can find a section for the twist. So I'm giving this easier version of things. So now I want to talk about Cartan pairs in the time that remains. So I apologize that this might have been slow for the experts, but I'm assuming that not everybody's an expert, including myself. So our goal is we want to know when we can recover our groupoid G and that cocycle up to cohomology, or more generally the twist, for those who know what a twist really is, from the pair consisting of the twisted algebra and the commutative algebra functions on the unit space. In the case, since a group is just a groupoid with one identity, the unit space has just one element. So the functions from a one element space to R is just R. So the Cartan, the pair that we would like to be Cartan is just the twisted group ring in R. And so we're just looking at basically twisted group rings up to R algebra isomorphism again. But in general, we want to preserve this algebra B. Okay, and we saw before for twisted group rings that the non-trivial unit condition was enough to be able to recover the group and the twist. So what is the correct analog of units in the groupoid setting? So we don't want to work with groups, since groupoids don't live inside their algebra as units in the same way that groups do. They're not the right answer. So it turns out you have to replace units by what are called normalizers, which form an inverse semigroup. I will not actually define an inverse semigroup because for this talk, you just need to know that they're a semigroup. But if you actually wanted to go into details, you would need to know they're an inverse semigroup. Okay, so what we also would like to know, which pairs A, comma B, consisting of an R algebra A and a commutative subalgebra B, arise from one of these groupoid twists. Okay, so here's our kind of general setup. So R is going to always be an integral domain, but in the paper, it's more general. It's just I'm avoiding some technicalities that way. A will be an R algebra, but not necessarily unital. I know Gene was one of the first people to study local units, so I think that this is the right place to talk about them. And B is going to be a commutative torsion-free. It's important that that B is torsion-free R subalgebra. So elements of R are not allowed to annihilate non-trivial elements of B. And it should be generated by idempotence. And it should contain a set of local units for A. So what that means is for any finite subset of A, there's an idempotent of B, which fixes that set F on both sides. So it belongs to this corner. This in particular means A has local units, but they come from B. This is kind of analogous to the analytic setting where you want the maximal commutative subalgebra to have some sort of approximate identity or something for the big algebra A. I think of local units as the algebraic version of approximate identity. So for instance, if you take the algebra of a groupoid twist, and you take the commutative subalgebra of functions on the unit space, you satisfy these conditions. And some more, which I'll be adding later. And I'm going to call these groupoid pairs. So pairs that come from a groupoid, I'll call a groupoid pair. Now I have to tell you what is a normalizer. So a normalizer is an element of A, which has an inverse in the inverse semigroup sense, or in the von Neumann regular sense, n prime. So it satisfies the von Neumann regular type condition that n prime n is n, and n prime n prime is n prime. And it conjugates B on both sides. You have to do it on both sides because we're not working with groups back into B. So people who do inverse semigroups run into this kind of stuff all the time. And because B is commutative and contains a set of local units for A, you can check that this guy is an inverse semigroup. Under the hypothesis of the previous section, this will be an inverse semigroup, a sub-semigroup of A. So it's a sub-semigroup of A. It goes under multiplications, and these conditions guarantee that it's inverse. The idempotents all belong to B, which is commutative, so the idempotents commute, so that makes it an inverse semigroup. For example, if I start off with the twisted group ring, and I look at the normalizer of R itself, So I have a twisted group ring. Let's just pretend it's RG, a regular group ring. And then I have R inside it. What are the normalizers? The normalizers are basically the units and also zero. Zero normalizes for technical reasons, right? Because zero is its own von Neumann inverse, and it sends B into a D for silly reasons. So you have to throw in zero, but those are the only normalizers you get. And so the normalizers are the right generalization of units. Another thing that's important is that a twisted groupoid ring is actually spanned by normalizers of a very specific sort. This is another thing you see in the Feldman, Moore, and all the other C-star Cartan theories that I am not qualified to talk about, but my co-authors are. So this is another feature. Okay, so to explain this, a bisection of a groupoid is just an open subset. So the domain and range maps are injective when you restrict to them. And it's important that the compact bisections form a basis for the topology of an ample groupoid. It's in fact equivalent to the groupoid being ample. For a group, a bisection is either empty or a singleton, because a group is discrete. So an open subset is just any subset. And since every element has the same domain and range, the only way the domain can be one-to-one is if you have a singleton. Okay, now there are some obvious normalizers which play the role of trivial units. If you have a function which the support is a bisection and it takes values in the units, you can check it's a normalizer. And that's the exact analog of the trivial units in this context. And so we say that a twist satisfies the local bisection hypothesis. It's a name I made up in my first paper where it was just groupoids, if the support of any normalizer is a bisection. So this is sort of so basically the kind of obvious normalizers I explained before are the only ones. And a twist on a group, the group case satisfies this hypothesis exactly when each unit has singleton support, because the support of a group element is just its algebraic support. It's the guys that appear in the sum. And being a bisection means it must be singleton or empty, or it could be zero. So this is a generalization of the only trivial unit hypothesis. There's also a nice sufficient condition. I'm not giving the most general one, just the one that I can state. So at any groupoid, in a groupoid G, you always have the isotropy group at an element X. It's just it's the automorphism group in the sense of category theory. It's all the morphisms from X to X, and that's a group. And if the set of points where the isotropy guy has the unique path property, the unique product property, or the set of guys for which this thing is left orderable, or actually where Kaplansky's conjecture is unit conjecture satisfied is dense, then automatically the groupoid inherits the local bisection hypothesis from these isotropy groups. So there's a better result than this, but the other one's more technical. So for instance, take the groupoid for a Leavitt path algebra. So in the groupoid of a Leavitt path algebra, all the isotropy groups are either trivial or infinite cyclic. Well, we all know how to order Z, right? Just the usual order on Z. So it's an orderable group, so therefore it satisfies the unique product property, it satisfies the Kaplansky conjecture. And the trivial group even more so. And so my sufficient condition of having every object has the property that you get this UPP thing, so you get the local bisection hypothesis. And so pairs where you get this that come from a groupoid, where you have the local bisection hypothesis, I'll call concrete quasi-Cartan pairs. And now I have to get into conditional expectations. So this is stuff the analysts like that, we just have to deal with. So I apologize to the Algebras, but I'll give you one example that you'll believe. So if you take a twisted group ring, there's a very natural thing which is sometimes called the trace, at least for an ordinary group ring, which, just chooses the coefficient of 1. Right? This is a standard retraction from the group ring to R. And it works for twisted group rings as well. And if you study this is the thing that makes a group algebra self-injective, and it's used all over the place. And so we want to generalize that for groupoids. If you're an algebraist, if you're an analyst, you already know why you want to do this. So let A and B be as in our setup. The conditional expectation is an R linear map from A to this commutative subalgebra B, which fixes B, and it's a BB bimodular homomorphism. So I can pull B's out to the left or to the right. And it's said to be faithful if for each non-zero element of A, I can multiply it by somebody on the left to get a non-zero guy. It's somehow in the context we care about. You can also multiply on the right. I'm not sure if you work like with really weird rings which don't have much like involutionary symmetry, whether you'd have to throw both sides in, but anyway, I won't worry about it because it works for our purposes, this definition. For instance, if you have a groupoid pair coming from a twist, then restricting a function to the unit space is a faithful conditional expectation. The unit space is clopin, so if I restrict the compactly supported function, it will be compactly supported. And this generalizes the group ring case, because in the group ring case, the unit space is just the multiples of the identity, and restricting to the identity is just taking the coefficient of the identity. And the general definition of an algebraic definition of the conditional expectation comes from Watanabe, as well as the faithfulness. In analysis, there's some analytic conditions that you have to throw in too. Okay, so suppose that now I can define what's an abstract quasi-Cartan pair. So this part's for the experts. So we have A and B as in our setup. So A is R algebra, B is a commutative sub algebra, A is spanned by normalizers, B has a set of local units, and all that other stuff. And torsion free, B is torsion free and generated by idempotence. And let's, oh, I didn't throw that into the setup. Sorry, I got ahead of myself. We're going to assume further that the normalizer spans A. That wasn't there before, but I'm adding that now. Sorry about that. Spans A over R. So every element of A is an R linear combination of normalizers, and there's a faithful conditional expectation. Then we're going to say that A comma B is a Cartan pair if B is a maximal commutative subalgebra. And we're going to say it's quasi-Cartan if you can magically choose this conditional expectation to have the property that the way it works on a normalizer is by multiplying by an idempotent. So for those who like inverse semigroup theory, this says that the inverse semigroup of normalizers is preserved by the faithful conditional expectation, and it's given by basically restricting. Okay? This is related to the Hausdorff condition on an inverse semigroup. This is exactly the kind of condition that tells you that as inverse semigroup groupoids associated to inverse semigroups are Hausdorff. This condition, this condition in the quasi-Cartan pair. So one thing you can prove is that Cartan pairs are quasi-Cartan. So this condition on the conditional expectation is automatically satisfied, and also the conditional expectation is unique. So there's only one conditional expectation, this faithful one, and so. And you can also show that a groupoid pair is quasi-Cartan if and only if you had the local bisection hypothesis. So for groups, that means no non-trivial units. Okay, so basically the abstract is the same as the concrete. And for those who know what this means, the groupoid pair would be Cartan if and only if the groupoid is effective. I'm not going to get into what that means because I'm running out of time here. I go to 7:30, you said, but I probably don't really want me to go to 7:30, so I'm not going to say what that means. So here's an example that every algebraist can understand. Let A be n by n matrices over R, and let B be the diagonal matrices, which just look like Rn. That's a commutative subalgebra, right? This subalgebra is spanned by the idempotence EII, the diagonal matrix units. The full matrix algebra is spanned by the ordinary matrix units, EIJs, and those are normalizers, with the inverse semigroup inverse given by just flipping IJ to JI. For those who like these things, the full normalizers are just the monomial matrices with entries in R cross. So these are matrices where you have at most one non-zero entry in each row and column, and that entry should belong to R cross. So sometimes this is known as the Reith product of R cross with the rook monoid, or the symmetric inverse monoid. This Dn of R, everybody knows, is a maximal commutative sub semigroup. Everyone knows this, right? And you have a faithful conditional expectation, which just takes the matrix to its diagonal. And so this guy's a Cartan pair. And it's the algebra of the groupoid with n objects and exactly one error between any two objects. So that's what our theorem says should happen. So now I can state our theorem with all the authors. Hopefully I didn't miss any. So AC cubed LMRS squared. You'll be tested on that. So let A comma B be a quasi-Cartan pair. So you won't remember the definition, but think that B sits nicely in A and B is like a maximal commutative subalgebra, or that all the normalizers are trivial. Then there is a twist over an ample groupoid G and an R linear isomorphism of pairs. So that means there's an isomorphism from A to this groupoid algebra that sends B isomorphically to the subalgebra. That's what I mean by an isomorphism of pairs. So it's an isomorphism which preserves the distinguished commutative subalgebra. So that means that basically every quasi-Cartan pair comes from a groupoid, and the twist is unique up to some obvious sense of uniqueness of or maybe not obvious sense of uniqueness of groupoid twist. And this is a generalization of what you have in the C star setting, or not generalization, analog. But the key difference is because of this unit stuff, we're able to replace the maximal commutative by this weaker condition that the normalizers aren't weird. So I like the title of this slide, How to Do the Twist. So I'm not going to give you any real details, but I'm going to try to give you a flavor. So if you have a quasi, as I see it, it's not exactly the way it's written in the paper either, but you know, everybody, probably every author has their own view on how to prove these things. So we probably have, I think, 9, if I'm correct, different views. So a quasi-Cartan pair, in my opinion, gives rise to an exact sequence of inverse semigroups in the same way that we saw for group rings. So in the group rings, we had we had this, sorry, I forgot where, oops, I didn't mean to save, all right, that was bad. So we had this exact sequence in the groupoid setting, you might remember, for twisted group rings, like this. So the corresponding exact sequence here is to replace the units by the normalizers. To replace this, these are the diagonal normalizers. In the case of a twisted group ring, those are the diagonal normalizers. And this is some quotient. So by definition of a normalizer, the diagonal normalizers are normal inverse subsemigroup. There's some definition of a normal inverse subsemigroup that goes back to the 60s or 70s, and you can take a quotient by one. And basically what I'm saying is that exactly as was done in the case of groupoids at the beginning of the talk, for these quasi-Cartan pairs, you can recover this exact sequence from the groupoids. And there's also a functorial equivalence. This part's not in the paper. We just kind of do it by bare hands, but I have a later paper that tells you exactly what the functorial equivalence is between appropriate exact sequences of inverse semigroups and twists over ample groupoids. So there's like a dictionary that goes back and forth. And so we can build a twist from this and convert. And if we actually came from if A and B were a groupoid pair with the local bisection, then this exact sequence is the same one that you would have gotten if you started with your twist and just went to inverse semigroups directly. And the proof that is basically very similar to what I did in the group ring case. It's very similar. But there's more ingredients because you will also need to know that if the twist, that the algebra of your pair, if your A and B did not come from a groupoid, you still need to know that the algebras A and B are isomorphic to the corresponding algebras. And there's some work. So one thing is there's a theorem of Keimel, I'm not sure how you say his name, he's German, who's funny, wrote a lot of stuff on semigroups actually back in the 60s and 70s, so I knew of his work from my semigroup days. He proved that if you have a torsion-free commutative R algebra over a domain, or slightly more generally, which is generated by idempotence, then it looks like locally constant functions on a certain uniquely determined locally compact totally disconnected space, which you can view as a Zariski spectrum or the stone space of its idempotence or its maximal ideal space or 100 other different spaces which all coincide. So using this and the conditional expectation, which plays a key role, and my co-authors know this stuff, I guess, from the groupoid setting, because I was very impressed how they could make all this stuff work. We can then kind of leverage this isomorphism of Keimel and the quasi-Cartan pair and the way you construct this whole thing from the inverse semigroup to get the algebra isomorphism. So that's sort of what happens. And so that's like all I have to say. I hope I didn't go too far over. So I left a lot under the rug, but that's because you really don't want to see the details.
Thank you. Are there questions, comments? Please feel free to unmute yourselves, de-video yourselves to show us who you are. Questions?
I have I have a question about what exactly is the relationship between I mean, Ben, could you go back and show us this page where the condition for that's it, yeah.
This
So,
one.
yeah, so Cartan implies quasi-Cartan.
Yeah, but it requires an argument. So you have to sort of show. It's a slightly clever argument, which I'm not going to remember off the top of my head, to prove that Cartan implies quasi-Cartan. There are certain kinds of tricks of playing with commuting stuff. It's not that different in some sense from the trick that to show idempotence commute in an inverse semigroup. Once you've seen it, you can kind of reproduce it, but I wouldn't want to have to reproduce it off the top of my head. So, I mean, I think originally there was a different proof, but eventually got boiled down to some clever trick that's showing certain guys commute, and that forces them into be inside of B. Okay. But the way I like to think of this is essentially when you have a twist, when you build a twist. Let's see if I can remember this. So now I have to go into the real definition of twist, but Hui knows what the real definition is. So if you have this kind of sigma, and then you have your groupoid G, and you have your R cross. So this is the central extension that corresponds to the twist, which is the real twist. You want something to know something about Hausdorffness. You want to know basically how can you see the Hausdorffness of say, how does Hausdorffness of sigma and G and all this stuff relate? And the magic secret is that if you take the inverse semigroup associated to sigma, the Hausdorffness of G is encoded by the fact that if you take any compact open bisection in sigma, there's a unique maximal compact bisection inside of the twist part started of the trivial twist, so R cross G, which is below U. And that idempotent is exactly the guy that this conditional expectation is picking out. So the Hausdorffness of the quotient is equivalent to, just like in an ordinary groupoid, being Hausdorff means you have a maximal idempotent below any element. To get that in the quotient, you need that the inverse semigroup of this guy has a similar property inside of here. So you have an exact sequence of inverse semigroups like ST, and then there's T mod S, this guy's normal. And what you need is that for everybody here, there's a unique maximal guy here, which is below it. And that's exactly the image of this conditional expectation. And that's equivalent to the Hausdorffness of G. So that's how I kind of see it, that you have to you need a maximal guy below it to get Hausdorffness on G. And so this, and this guy has to pick that guy out. I don't know if anyone else thinks about it that way, but that's how I think about it.
But the other point is, where exactly does the fact that every normalizer is supported on a bisection show up? Are you assuming that, or are you proving it?
So if you start with an abstract quasi-Cartan pair, then you have to prove this kind of stuff happens. If you start off with a groupoid, you assume that for groupoid, if you're given a twist on the groupoid, it can be quasi-Cartan if and only if you have that local that every normalizer is supported on a bisection. To go the other way, that essentially ends up getting proved in the course of things.
Okay.
But you really need that condition in order to guarantee that the diagonal normalizers are the inverse semigroup corresponding to this groupoid. The local bisection is what tells you get the right inverse semigroup there. Otherwise, the inverse semigroup in the exact sequence is not the right one to build a twist. So the local bisection condition, or more generally the quasi-Cartan condition, gives you that you get the correct diagonal normalizers. The only diagonal normalizers are, from the chimal point of view, guys which are kind of take values that are either units or zero.
Nice.
So that condition is real, but of course, I mean, I don't know of a C-star version of that condition, because because when you start completing, I think the normalizers probably get much more complicated, and I don't know, how to leverage that.
Renault has a result that says that on an etale groupoid, on an etale Hausdorff groupoid, every normalizer is necessarily supported on a bisection.
You don't need to assume effective?
Yes, of course.
Yeah, but if you want to go beyond effective, these quasi-Cartan guys don't have to be effective. Like any graph, any path groupoid, even the non-conditioned L ones meet this. So I don't know whether for Hausdorff groupoids, if you go to the C-star algebra, if all the normalizers are supported on the reduced one, I guess. I don't really actually understand anything about the reduced C-star algebra, so that's why I don't really think about it, because I can, as I said, I can pass the multiple choice test, but not the real test. Because
I don't think that will ever happen in the.
That's my guess. That's my guess is you get way too many normalizers if it's not effective. I mean, I don't think you have any analog of the no non-trivial units either in a reduced group C-star algebra.
Sure.
So I think that this is somehow something that's algebraic, this ability to go slightly beyond. That is a weird consequence of the no non-trivial units business, which works for groups.
Right. So,
I should say Carlson and Brad were the first to realize that was important.
I have one extra comment, which is that several years ago, I wrote a paper in which I discussed Cartan pairs in which the subalgebra is not necessarily commutative. And there was a lot of work in order to get your condition of quasi-Cartan with the conditional expectation. So I would say that if you rephrase your axioms in such a way that B is not necessarily commutative, but if you retain that assumption about the existence of this idempotent defining the conditional expectation, you might be able to get away with the lack of commutativity of the subalgebra and perhaps prove it. Of course, you won't be able to get a groupoid, but what you would get a sort of a Feldbundle over an inverse semigroup.
Yeah, I expect the cross product of some sort or a Feldbundle kind of thing, which I think Tristan Bice has been looking at these kinds of objects, but I don't think he's done an exact theory of Cartan pairs, but he's definitely been looking at groupoid bundles over inverse semigroups. I was looking at sort of more conventional cross products. You can write this twisted algebra also as an inverse semigroup cross product. There's an algebraic definition, which is not so different from what you did with Alcides. I think the axioms are slightly different, but they more or less have the same effect. And so probably one can do something more if you're willing to work with more complicated, concrete stuff. We certainly haven't gone there. There was also some discussion, particularly by Gilles, I think, of moving on to the non-Hausdorff case and then getting rid of the ideal of singular functions and working with sort of the essential algebra. That also seems like a possible reasonable future. I mean, because again, the twist, you don't really need Hausdorff to define them. You don't really need them to define the algebra. And even recovering the groupoid from the inverse semigroup exact sequence you can do with that, the Hausdorff condition. But then other things will, of course, break down because anything that relies on conditional expectations will, I guess, have trouble. So I don't quite know how the Cartan pair works in your more general setting yet, but anyway, there was some discussion about looking at that as well.
Okay, thank you.
Are there other questions?
I see there's some questions on chat, which I've not been reading.
I don't see those, sorry.
I see some questions. Oh, they're direct messages to me. Probably they were meant. Am I allowed to read them, Alexander?
Yeah, I didn't want to ask if they may be like stupid or so. So like.
So to get a Cartan pair, you need that. You just need the groupoid to be effective, which is slightly weaker than principal.
Yes.
There's something for principal, which we call diagonal pairs in the paper. I didn't talk about it in the talk, but so there's a stronger property that you ask that they be spanned by normalizers whose squares are 0, which is analogous to what Kumjian does, and then you can get then that corresponds to the groupoid being principal.
But it's kind of like necessary, right? I mean, like so, like to get a nicely Cartan pair, like in your sense.
So I mean,
Like you
Renault
will
does
need
a theory of Cartan pairs where it's just maximal commutative. He doesn't require that stronger condition. But I'm not enough familiar with the operator world to know why you would want that extra diagonal condition versus just the general maximal commutative condition. I mean, the maximal commutative condition seems to be enough to get the kind of properties we want. And that's certainly like what happens in the case of these groupoids that come for graph C-star algebras and Leavitt path algebras. Those groupoids usually are not principal unless I guess you have something like an aperiodic shift or something like that. I mean, no periodic points or something like that, or eventually periodic points. The inverse, you were asking about the inverse semigroup normalizer thing. So the only people I know of who used inverse semigroup cohomology and exact sequences of inverse semigroups to study analysis was work by David Pitts, Alan Donzig, and I think there was a third author, where they were looking at Cartan pairs of von Neumann algebras, maybe not necessarily assuming separability or something, and they exploited essentially that there's some inverse semigroups there, and that things are determined by a cocycle in the sense of Lausch. And the same thing is true for a groupoid twist over an ample groupoid. It's determined by a cocycle in the sense of Lausch. It determines the twist up to equivalence. And it's, the argument's actually very similar to what they do. And actually, what they do also explains something in one of Rui's papers I didn't understand, which is in his definition. I don't even remember this when he defined cocycles for doing your cross products without see this. You talk about this Kumjian condition. And this Kumjian condition is exactly a condition that Pitt and Donzig look at, which is that your exact sequence of inverse semigroups have an order preserving section, which is exactly equivalent to the groupoid having a continuous section, which it doesn't have to have. Donzig and those people wanted an example of an inverse semigroup where you don't have an order preserving section, and they exist. But they're in that unpublished thing that we have notes written on.
So like, you mean like a global section?
So in order for a twist to really come from a cocycle, the way I wrote, you need a continuous global section, and those don't always come for ample groupoids.
Yes, exactly.
And this can be phrased entirely in terms of inverse semigroup. It just means that the exact sequence of inverse semigroups has an order preserving section, not a semigroup homomorphism, but an order preserving section. In general, you have a set theoretic map, but not an order preserving one. And this is equivalent to the cocycle satisfying this Kumjian condition in Hui, and I'll see this as paper.
So you say you can rephrase coming from a global section in terms of the
inverse for ample groupoids. For ample groupoids, yes.
I see.
So coming from a genuine locally constant cocycle is a condition on from the inverse semigroup world, or it can be rephrased that way. I mean, that's not surprising. Basically, ample groupoids are the same thing as a Boolean inverse semigroups in some sense, so it's not surprising. And the twist is just throwing in extensions, central extensions of inverse well, not central, but something, they're not actually central, but they're extensions of inverse semigroups.
Okay, yeah.
So I hope those answered your questions.
Yes, I also had like an, sorry, can I ask another question?
Other questions?
Can I ask another question?
Please.
Sure.
So, so I've been wondering, like, I'm like, you know, like, I'm like, you were also like trying to figure out like which kind of like, kind of like pairs of ABs like come from groupoid algebras, right? That was like one motivation, if I'm not mistaken.
So I mean, these are algebraic algebras, not C-star algebras here. So I mean, I know that some people have tried to define analogs of Kirchberg algebras in the algebraic setting, but I'm not sure how successful that's been. Maybe Gene knows more about that.
I can't offer any additional information. Maybe Mark?
Mark might be getting coffee or something. His video disappeared, so he might have left the building, as they say.
Well, I guess, I mean, all Kirchberg algebras are C-star algebras of ample semigroups. So they have an immediate generalization to the algebraic case. You simply take the Steinberg algebra of the same groupoid that gave you the Kirchberg algebra. So of course, that's not a definition in terms of properties, but it does give you a way to define them.
And are we get? But is there any sort of uniqueness to the ample groupoid, or could we might by some luck get two abstract algebras with the same C-star completion?
Don't think so. I mean, I haven't really thought about this, but of course there are many properties of the groupoid which characterize the purely infinite property, separability, and so on. So it's it shouldn't be so hard once you.
Yeah, so people definitely try
to
to define analogs of the proproperties. I'm not sure whether there have been analogs of the results. I mean, there are these weird things that happen, like I guess if you take if I understand this correctly, if you take tensor products of like ONs, you don't really get anything exciting in the C-star world, but in the Leavitt algebra world, you get higher rank graph algebras, which are more complicated things. So there are some weird, of course, that may be a function of the completion of the tensor product that's going in there, but so it's not so clear if the worlds act exactly the same. I should say also, if you like higher rank graphs, that the same stuff that I just said about Leavitt algebras would be true for them as well, because their isotropic groups are free abelian, so they're orderable, and therefore they also automatically are quasi-Cartan. For those who like higher rank graphs, which again I can pass the multiple choice test, but not the written exam.
So you say like for higher rank graphs, you always get a Cartan pair?
No, quasi-Cartan. That's the difference.
Quasi-Cartan pair?
Yeah, because all the isotropic groups are free abelian, and free abelian satisfy the Komplensky unit conjecture. Mm-hmm. But to get the maximal thing, you need the analog of condition L, which I forget what it's called. I've seen something with the letter A involved in it or something. It's in some of Aiden's papers and other people's papers, but I don't remember what they call it.
The A is for aperiodic, and it is similar, yeah.
Yeah, so there's a condition that's an analog of condition L for higher rank graphs, which gives you the effective groupoid and the Cartan pair in the C-star setting. But in the algebraic setting, you don't need it because you get it for free. Because of the isotropic group being free abelian. That's just like a wonderful thing from the point of view of this, because the free abelian groups still live in the world where Komplensky's unit conjecture is true.
Other questions, comments, remarks for a speaker? Well, if we would all unmute ourselves, we can give the speaker a brief round of applause. Thank you very much, John.
Thank you, Gene.
So our next talk I can't officially announce, but it will be in the fall, and you will get an email as to when it will be and who the speakers will be, and as to what the setup of the Algebras and Rings in Colorado Springs algebra seminar will look like in the fall. But I appreciate your attendance here. We will post the recording of this talk on the ARC's website shortly. That might mean within the next few hours. And I hope that you all enjoy the rest of your day or evening, depending on where you are. And we hope to see you soon. Thank you very much.
And the multiple choice test is tomorrow. No. Bye, everybody.
Thank you, Ben.
Thank you.
Thank you.
Good
Bye.
to see some faces I haven't seen in a long time. Okay, I got to run off. So take care, everybody.
Thanks, Ben. I appreciate
Bye.
it.
Bye, everybody. I do have to run off. So I'll see you. I have 2 of these to leave.